Dear colleagues, my name is Konstantin Morozov. Let me present you generalization of the formal method of determining the state of processors of multiprocessor system under testing. Control systems of complex and especially critical objects whose failure may lead to significant damage usually have increased requirements for both performance and productivity. Both these requirements may be met with using so-called fault-tolerant multiprocessor systems. The systems capable to remain operational even if of failure of some of its processors. One of the fault-tolerant multiprocessor system developers' problems is testing of it. That is, in other words, determination of states, operational or faulty, of each processor of the system. There are two main approaches of testing of such systems. The first approach is based on the usage of dedicated node used for testing. This approach is relatively easy for implementation. However, it uses additional node which also may fail, and it may become a bottleneck of this approach. It seems good to be used for testing the system at the stage of production or service. The second approach is based on cross-processor testing. Here, the process of testing and especially state determination may be much more complex. However, it doesn't require additional nodes, so it may be preferable at stage of system operation. The approach to be presented is related exactly to the second type. This suppose the testing of the system is performed according to Preparata Metze Chien model. According to this model, there is a pair of processors, a testing processor who tests a tested processor. The result of the test check will be 0, no failure found if tested processor is operational, or it will be 1, a failure found if tested processor is faulty. However, it is correct only if testing processor is operational. And if it is faulty, the result of the test check may be 0 or 1 independently from state of tested processor. One other important concept is undiagnosed system. In this case, the state of system can be established by executing mutual tests, checks of processors only in case if the number of their failures doesn't exceed the value m. So it's a undiagnosed system. The possibility of mutual testing of processors of the system can be represented as a directed graph like this. There, each vertex corresponds to a processor of the system, and the arc from the vertex A to vertex B corresponds to ability for processor A to test processor B. This graph describes capabilities of system in terms of diagnostics. The goal of the research is to determine state of each processor, operational or faulty, from results of mutual test checks, which are done according to PMC model. It has been proved it is possible if less than half of all processors of the system are faulty. It's described here. However, it also was shown that almost always it is possible for more values, more number of values. There are also exist an algorithm allowing to do it based on the execution of no more than n plus 2 times p test checks, where n is total number of processors and p is number of actually faulty processors. However, all this is applicable only for complete graph case. Unfortunately, real systems not always correspond to complete graphs. The approach that may be used for arbitrary graphs was proposed. Let's consider so-called state vector of the system. Its elements are Boolean values corresponding to state of each processor of the system. The value 1 corresponds to operational state, and 0 value corresponds to faulty states. Let's denote these values as variables x, y. So here will be variables. We can build a constituent of 1, a conjunction containing all of variables xi with inversions or without inversions, and each constituent corresponds to some state of system where variables without inversions correspond to operational processors, and variables without inversions correspond to with inversions correspond to faulty processors. And only for real state, the constituent will be have a value of 1. I mean, for state where these values correspond to real state. It is shown in paper. And it is also assumed that the system is diagnosable. For each test check, it's proposed to build some expression according to result of this text check. It will be this or this, depending on the result of this text check. As I said, test checks means testing of one processor by other processor. It will be the result according to PMC model. For all the expressions from some test set, the expression that is conjunction of expressions corresponding to separate test checks is built. So we get all these expressions and build a conjunction of them. Then this expression is transformed to a perfect disjunctive normal form, that is disjunction of constituents of 1. And moreover, the conjunctions having more than m inversions are excluded, and we can do it on all steps of transformation. After these transformations, there may be 3 options. The constituent, the one constituent is left, more than one constituents are left, and no one constituent is left. Here is interpretation of these 3 cases. For case of single constituent, this constituent corresponds to the real state of the system, and the variable, as it was said, the variables included in it without inversions correspond to operational processors, and all the rest processors are faulty. For case of more than one constituent, the state cannot be unambiguously determined. However, the constituent corresponding to the real state exists among them, so additional tests may be carried out to determine it. For case of no one constituent, more than m processors have failed in the system. But the opposite is generally not true. Depending on the combination of test results, any of these 3 situations may be possible. But for case when not more than n processors have failed, we will get this or this one situation. However, we can generalize the proposed method. Let's use result of some test checks in generalized form. Instead of selection of some expression which depends on test check result, we will use generalized expression. It contains result of test checks as variable Rij. So test checks may be not conducted at this moment. We can perform test check after transformations. And at the same manner, we build expression containing conjunction of all expressions for each separate test checked, and it may be done either after some initial tests conducted or from scratch, even from scratch. In this case, this value will be just 1, not an expression, just 1. Then we can transform this expression to PDNF-like form. However, we will split it into constituents which contain variables x, y, and coefficients which contain variables r, I, j. And there are two statements for this form which are proved in the paper. The first one is if for any two different coefficients, their pairwise conjunction is if their pairwise conjunction is identically equal to 0 for any two different coefficients, then the considered set of test checks is sufficient to ambiguously determine the state of the system in case of failure of not more than m processors. So if all these coefficients, all these pairs of coefficients always give 0, then this test set is enough to determine the state of system. It's we can use this test set to unambiguously determine the state. And the second one statement is if the condition of previous statement is satisfied, and it means this condition of this statement is satisfied, and for some combination of test results, one of the coefficients acquires a non-zero value, then the state of the system corresponds to appropriate constituent. So we just need to find a coefficient that will be non-zero, and then we can just take appropriate constituent, and it corresponds to some state vector or some state of system. So let's consider one demonstrative example. And in the original paper, you can find more examples for different cases. Here we will analyze only one simple example. Here we see one diagnosable system, and its graph is presented on the slide. We can form the expressions for each test check, and we form the conjunction and transform it with excluding all conjunctions containing more than m inversions in part of constituents. So we obtain expression containing 5 members. The whole transformation process is skipped here, but you can find it in paper. So we obtain 5 members, and we can form 5 coefficients and 5 constituents corresponding to them. We can ensure that these coefficients match the statement considered before, the first statement considered before. So these test checks will be enough to perform, to obtain a state of the system. Then we can build a table of correspondence of combination of test checks results to values of system state vector. So according to for this test check results will be this system state vector, and these values correspond to any result of test checks. So if we have these 3 values, then the state doesn't depend on result of this test checks. So we can just exclude some checks if we find this situation, and in this case also we can skip this test check. So the following conclusions may be formulated. A generalization of the formal method for determining the state of processors of a multiprocessor system during testing was proposed. It allows to analyze a combination of test checks before executing tests. It's important. For each admissible test state of the system, a certain coefficient can be determined. Coefficients consist of the values of the test results. And criteria of sufficiency of combination of test checks are formulated. And also it should be noted that the proposed approach can be used to search an optimal set of test checks. And one of the advantages of the approach is implementation of complex transformations can be transferred from the stage of self-testing to the stage of system development. Thank you for your attention.